10 minutes?
Yeah. Oh, you're going to do it in Spanish?
I did the slides in Spanish because I don't have time yesterday, but I could make the.
Okay, well, if you want to talk Spanish, it's better, but then I can't understand.
No, que mejor en inglés, diferente. No. Idealmente en inglés.
So, yeah, I can give you like a warning like in 5 minutes.
Okay.
Sure. Then just for everyone, let's try to keep the 10-minute maximum so that we have time. And I don't know, like the people that are not here, maybe we can squeeze them in later.
What, sorry?
So there are a few people, like the people that were supposed to go first, they're
Yeah.
not here yet, so we'll see what happens. Can you switch on the lights?
So you give a warning when there's
Yeah.
5 minutes or 10 or 1 minute?
1 minute.
1 minute.
Oh, that's a 9-minute.
It's good? Yeah.
So I take the paper about the dust masses in the known list by typewriter. I'm going to start. Sorry if the presentations are in Spanish, but I don't have enough time yesterday to prepare the slides. But we are going to start talking a little bit about non-stellar objects, because in the article they try to find the goal of the article was to review that in class 2 stellar objects, the mass of dust found in there is not enough to go with to represent the actual population of exoplanetary systems. Yeah. So just to make a little review, when a star collapses, we can see that the non-stellar objects can be classified by class 0, class 1, class 3. Depending on the SED, the spectrum energy distribution. In this phase, the star is still in the envelope of the gas, yeah, and it's collapsing to the top, and we can see here. And this is a representation of the SED, so you can see more or less how is the evolution of the planetary disk. All these slides and information was taken from a review taken by Williams in 2011. That is a good review about the protoplanetary population synthesis. So it's a good review if you want to take a look about how is all the process about the planet formation, the population of exoplanets, how is made the planetary synthesis, etc. So in the past, we always think that in class 2 is when the protoplanetary, the disk is start to become protoplanetary and not stellar, yeah, in the pole. I don't know what happened.
Oh, maybe it was just my screen. Sorry.
Okay.
I think my screen was. I'll change it to the settings.
Okay.
Yeah.
So we think, or all of the reviews that we take is from class 0 to class 1 takes more or less all that 5 million years. And in this phase, this is still considered as a protostellar disk. Yeah, it's still all the material is fluid to the star. But we think that in class 2 is when the disk is comes to taking planetary. But with the recent results and new measures, uh, the mass of the dust in some planetarities, protoplanetarities, is not enough to represent the actual population of protoplanetary systems that we found on our observations. So the team with the paper that is, if there is not enough material to represent the population of protoplanetary systems, maybe the planet formation begins in the earliest stage of the formation of the stars and the planets, etc. So they made a lot of give me a second. Yeah. So the idea is they take into account a lot of measures and observations with ALMA and BLA to measure the mass of the dust in the class 0 and class 1 young stellar objects. They take observation in ALMA for 44 protostellars. 44 class 0 and class 1 protostellars, and review in the 1.1 millimeters and in the BLA. And the idea they take is to compare those observations and take a measure of the dust on that forget the word. So, to take the measures on that objects, class 0, class 1. But the thing they first has to compare or calibrate the observation with BLA and ALMA, because with the BLA they have some contamination due by the free emission. So they make some corrections in the observations, and they want to be sure that corrections were accurate. So what they, in the paper, I don't put here all the procedure, but they explain how can make the free emission and how they validate the corrections that they make and get to the result that was the sources that they measured with annual BLA was from the same source, from the thermal emission of the dust. With that information, they found that the correlation between the ALMA is here is the both measures with ALMA and BLA, and they found the correlation that has a good slope. So they assume that the both sources came from the same physical process, the same thermal emission of the dust. So when now they know that the measures or the sources are calibrated, they start to measure the mass of the dust with this formula. Yeah, this is the distance of the source, the V. They use, this is the flux. They use the kappa for ALMA, 1.2 millimeters, as 3 centimeters squared large. Okay. And at temperature, they assume that all the disks have is isothermal and have the same temperature for the dust. And they put it at 30 Kelvin, because there is another that make the temperature dependent of the values, depending on the opacity and everything, so they can change a lot this particular masses. So they assume these parameters, calculate the mass of the dust, and they found that in this is what's in Celsius, and they found that with ALMA for class zeros, non-stellar objects, they found that the mass of the dust was 47 Earth masses. For class 1s, 12 Earth masses, and class 2, 2 Earth masses. And for the VLA, it measures 158 Earth masses, and for class 1, 52 Earth masses, and class 2, 2 masses. So with these results, they can be sure that the mass contained in the class 0, class 1 non-stellar objects is enough to create or to create the actual exoplanets system that we found on our observations. These graphics show us how are the exoplanets. Yeah, this is the top of the class 0 mass, class 0 1 masses, and here are the masses of the exoplanets and the population or system of exoplanets that we found, and they can correlate that indeed the planet formation starts in the early stage, not in the class 2 as we think in the past, but right now we know that even when the star is forming and when everything is collapsing, the planet formation can start to be important. And it's a lot of another characteristic or evidences that tell us that this is happening because there is some structures even in the class 2 that represents that some planets have to be there before the class 2 begin. Some meteorites in our solar system that has some composition give us an idea that this formation of exoplanets can start in the early stage. And yeah, I already told the conclusions. So, okay,
Yeah.
this is all. Thank you very much.
Any questions?
Yeah, questions?
Who's the next victim?
So is Anye or Danielle or Alejandro
Vale.
here with us? No? Valeria? Oh, only first session before I was here. Sophia.
Sophia or Ana Sophia?
Sophia.
Arboleda.
Arboleda. That's good. No?
Yeah.
Yeah, you are here? Okay.
But I haven't sent you yet.
Oh, okay, you can send it now and I'll start. Also for the other.
Okay, then I have a question
Yeah.
for Sebastian.
Yeah.
So why is there a difference between dust masses calculated with PLA measurements and ALMA measurements? Are they measuring something different?
They assume different kappas and betas. Yeah, because one is for 9 millimeters, and so they explain. I don't know about the radioastronomy, but what the difference in the opacity assumed for the calculation of the mass. So as you can with this equation of the mass, yeah. If you change this kappa or the flux are different, the masses are different.
Yes, but are you looking at the same type of dust?
They only say in the paper that they are pretty sure that is the emission that they are receiving is from the same source, yeah, the same thermal, the same physical process. But I'm not really sure if it's the same size of the dust or work velocity, or I don't know. Maybe it could be another type of dust.
Okay.
Yeah.
But I'm not sure.
Okay, so indeed, the kappa is of course different at the two wavelengths, so that also the flux and the Planck flux are different. And you can actually see it in this plot, right? If you look at the mass distribution of class 0 and class 1 in both plots, so in both wavelengths, is the same. So what they're essentially showing is that the dust is optically thin in the at this wavelength. But for the class 2 sources, we see that there's an offset. So there, they essentially argue that the ALMA data must be optically thin. So it's underestimating distance. So that's why they do both ways. It's essentially to check this assumption of optically thin.
Yeah, they made pretty clear in the paper. You have to assume that it's optical thing, but I forget to say. But yeah.
Sorry, and I'm actually saying it the wrong way around. Sorry, it is the class 2. The class 2 is fine. Sorry, I was saying it completely opposite. The class 2 is optically thin, but the class 0 and class 1 are not. Reversing.
Okay.
Sorry. Yeah. And it makes sense because in the early stage the emission is much more compact, so it's more optically thin. Okay. You can see that by comparing these things.
Yeah.
It's a good lesson. Don't assume that it's optically thin. You can sometimes, but then
But that's not always.
Yes.
Yeah. And about the size of the dust, they don't make to be another rules.
Malaysia, I don't have your yes.
Maybe someone else will begin, I'm not exactly.
She's having trouble with internet.
Oh, okay, sure. We can go to another one. Frank.
Frank.
There is a go.
Sebastian?
Yeah.
Where's the speaker?
So my name is Michael Pista, and this was a paper that I choose. Homogeneous analysis of the dust morphology of transitional disk observed with ALMA. Investigating this graphing and the origin of cavities. This paper was published in 2018 by Juanita and colleagues. And basically, this is a large series of papers about the dust graphing and the origin of cavities. In fact, this is the second paper that they published. So, let's talk about transitional disk. So let's remember that this concept of transitional disk. So we have a gap or a hole in a disk. So we consider that a transitional disk, but remember that it's not necessarily that this is a sign of evolutionary term. So we can accept the explanation that this material in the disk have a lack of optically big. So we can just consider a transitional. As we saw in the lectures, there are some characteristics like the cavity size down to 2 astronomical units, to the 30 astronomical units, but in this paper they consider also 45 astronomical units. Also, they have some inconsistency in the transitional disk because, well, there are some criteria to consider one or another, you know. So let's remember this, that the transitional disk has a cavity or can also have a cavity and a disk or some bumps or asymmetry. But in this paper, they just analyze cavities, no rings, no clumps, no asymmetries, because they just want to narrow the explanation of these cavities. So they took observations from 2012 to 2016 of these transitional disks, and just with a cavity, without rings or other things. And they perform cleaning, and also they get the center and the position and the inclination of this disk by using CASA. And this is the results of these 29 transitional dilatations for this stack. So, what was the idea? The idea was fit the millimeter dust continuum by a Gaussian expression. In fact, a radial or a ring expression of the visibility. So they consider different how do you say that? Width of the cavity, internal width and external width for the radius. And they also have the projected data for the visibility plane by a Fourier transform of the brightness. And they just take the brightness in the real part by this constant. You know, this explanation, this math explanation is better or well related in other paper, in the previous paper of this one. They made all the calculus. What was the idea with this math? Basically, they took this math in order to so the idea was to this math to make Markov-Chain Monte Carlo and CNC method to fit the observations, or well, fit these models to the observations. So we can see here an example of this fitting. And with these distributions, they get the optimum parameter for this method. So they just take autocorrelations around 100 steps in the MCMC methods, and but also to determine well these parameters, they also obtain 700 steps of this MCMC. They leave free these parameters, with the radius big, the width of the cavities, and the total flux. And after that, with the optimal parameters, they just show a linear data corresponding to the real part of the visibilities, which is in black with these uncertainties. And also overplot the model that they get in red for the 29 transitional disks. But with these ideal parameters, they also make the profile of the intensity. Do you remember the intensity with this Gaussian ring? So that was the idea, these intensities. So that they say, well, let's say that the cavity sizes are different and also are so, what do you say? Some are symmetrics, but others are truncated. And this is the profile of these cavities. So we can say maybe that there are large cavity sizes. So we can say just put one together in the model. I mean, just take the model as one for each one. I mean, take one as ideal. So after that, and with it in mind, with the intensity normalized, they just make some analysis results. So as I told you, with the flux and the MCMC parameters, they calculate the dust mass and the relation of the star mass with the mass of the dust, of those masses. And they say that this relation is flat. I mean, they don't grow, when one is grown, the other grows too. No, they find this is flat. So maybe in theory, we can say that are directly proportional, like planetary formation could be. And also, they analyze the correlations for the cavity for the stellar mass, the dust mass and the masses normalizes. And they say that there is no clear correlation for the data. So we can say just is some pattern. No. So the most clear is that maybe transitional is with cavities of 45 astronomical units around low masses. It could be possible, but there are no correlations in the results. They also have more results, but are not essential for this paper because they say, well, we are continuous studying. So that was the most relevant in this paper. So what this is that what we conclude basically that the relation with the mass dust and the star mass is much flatter from the observed that the theory said. The possible reason is because the emission is optical deep, or the particles are rapidly pressure bound. Also, well, that there are diversity cavity sizes, as I told you, and structures, and they can be described by using this Gaussian method. There are not transitional disks with very large cavities around low masses stars, as I showed you in the previous plot. So that was the paper, and they continue. They have another 2 or 3 papers about this part.
Thank you.
Some questions?
Yeah, so the sensor is here, so if you stand there, it's definitely, yeah, no, it was because I moved it a little bit, so it should be,
Well, don't
is
worry.
it working now? Yeah, it is working, it just, you need to be in view of the sensor, so that was it.
That was it.
Yeah.
Okay.
But,
No.
so, okay, well, maybe just go back, sorry, because I have a question. So how did they select these transition disks?
Well, as I told you here, they selected by study that this just was this a cavity, just a cavity, not an inner piece, not a symmetry.
But how did they know that?
Because they tried the by ALMA, they clean the data and they consider with the UV model fit the center of the position and consider just targets with these characteristics.
Okay. Yeah. So they remember that the ALMA archive contains lots of data, right? So what they essentially did was browse the archive and browse sort of published work to see which transition disks were there. So this is what I mean with how did they select it.
Okay.
It's not like they didn't select it from SEDs, or like they didn't write a proposal and get data. They actually used archival data to construct this entire sample.
Okay.
So this is something, yeah, it's okay. I was
But
wondering if you pick that up.
But also because the SED will not have that information.
No, so it's some of these, the SED that actually doesn't show it. So, no, in this case, it is not to create the largest possible sample of transition disks based on what was available in the archive. And you actually see that there is several papers that use this approach. Because if you apply for all that time, yeah, there's a pretty low success rate. You have to wait a long time to get your data, and there is already quite a lot of data in the archive. So you can construct your own study based on or your own sample by combining multiple data systems. Do a study. So that was really their goal, to see, instead of doing all an individual, like many individual studies, to see what do all these disks have in common. Next. Yeah. I know this is really not criticism, but I just want to clarify this point.
Okay.
Next, and Larry? Oh, no, sorry.
No.
No,
Yeah.
what did I say? So it's Sophia, sorry, it's Sophia.
Do you have it there already? Esta ya la presentación en principio. Sí, ven por aquí, yo sé que. Bueno, te lo digo. Pero qué era el pantallazo más rápido.
Sorry, Sophia, is this the right file?
Yeah.
Okay.
Ah, ok. No lo voy a dejar pasar.
Okay, so here's the, so, yeah, that gives you, that's the laser.
Right.
You point it that way. See, and then there's the one to the left and the right is forward and backwards. So, yeah.
So the paper I choose is one from Inke. It's all. And it's a major symmetric asymmetric dust trap in a transition disk.
Okay, I'll just do it. Sorry.
So this is in the context of radial drift. I don't know if you remember that we talked about the problem of radial drift in formation of planets, or in planet formation, or even smaller, like in centimeter-sized black holes formation on the other planetary disk. And so we talk about radial drift as a problem because it was an inward drift for particles, and the fragmentation because of high velocities was also a problem of the formation of bigger particles in the other disk. So one solution to that problem was the dust trap. So the study was one of the first studies of ALMA in the early cycles zero. Yeah. When there was only a quarter of the antennas that ALMA currently has. And so the study found a highly asymmetric concentration of millimeter-sized dust on one side of the disk of IRS 48, which is disk around a early star in the features forming a star region. So this A-type star was really well studied, and it was known to have a large inner cap. So I'm gonna talk a little bit about the results. The observations of the 4-7 mm CO1 showed a ring of emission at 30 AU radius, and we can see here the simulated in the previous. We saw the real data and the continuum from L1 data and the emission in the second one. And in this one, we can see the simulated data of the continuum. And in that part, we can see the normalized logarithm as well as a little cut of the peak equation. So you can see there's actually a peak equation in that part. And it was also studied the CO65 spectrum and how was the emission of CO in that region, and they found that there was a Keplerian disk profile. So we can see here the emission, the blue dotted lines indicate the like the shifted in blue and the shifted in red, but not that. And we can see a simulation, like a cartoon of how the planetary disk would be with a accumulation of rain in that south part of the disk. And there was also a simulation with Fargo, a hydrodynamical simulation that considers a companion, a substellar companion of around 10 Jupiter masses, and we can see the simulation that responds to the observed accumulation produced emission. And we can see here also a simulation of the pressure trap and with the 10 Jupiter mass planet. And as we saw, we can see the gap opened by that planet and the pressure trap near that gap. So, in conclusion, the drop of the gas density at the 25 more or less astronomical units, and the radial drop of molecular dust emission in 45 astronomical units suggests a substellar companion, and it is between 20 astronomical units and around 10 Jupiter masses. And the total dust emission corresponds to 9 Earth masses. And the dust drop could initiate formation of a hyperbelt around the star. So that was the
Thank you. Any questions? So, how do they estimate? Sorry, how do we estimate the 10 planet? Why do we know that it's 10 Jupiter masses? Where does that come from?
Maybe that's with
Yeah, the drop in density. Sorry, can you guys hear? Because there's noise on the corridor. Oh, you already closed the door. Never mind. Thanks. I'll just say it. It was very noisy even on this side, so I figured it was even harder for you.
I can hear.
You can hear it well? Okay, perfect. Thank you.
I think the major problem is that it's
Okay, then we just switch that up. Too warm. Ooh. If it gets too warm, we can switch it on again. Okay. Yeah. So, if there's no other questions, you guys can ask questions too. Then, thanks, Sophia. And we're going to see who is next. I guess Melvin. Yeah. Oh, okay.
Que lo agarré
No se lo
mil
haya.
veces.
¿Cómo yo puedo hablar? No sé.
No, es que es para la grabación.
Ah, ok.
sí, ¿Tiene un acento? Pues no.
Presentamos ella.
Sí. Y me acaba aquí en medio. No, entonces, un momento. Para subirle esto a la sensibilidad. ¿Y quién habla más alto de los dos? Creo que dos. Entonces, te vas a poner tú. Eso. Esto es un bolsillo. Y voy a usar la pincel. Vas a procurar hablar más del tono, ¿sí? Y no se separan. O sea, idealmente los dos son de una vez. Eso. Y pues, en la cabeza. Eso. Dale, sí. Listo. Los dos mismos. Cuando hables, como. Listo.
Well, hello everyone. We're gonna.
Oh, you want the clicker? It's right here. And if it doesn't work, we just say next. I'll do it. Yeah, it's because the sensor is, yeah. Just say next. I'll do it. Go ahead.
Okay. Hello everyone. We're gonna talk about a review of a paper of Andreisela et al. Of 2016 about the ringed structures of the HD 163296 protoplanetary disk with observations made by Alma. Our names are Melkin and Marcela. Let's start.
Okay, so HD 163296 is a Herbig AE star located at 122 parsecs from Earth. And Herbig AE star is a young star that has an spectral type A or B, but they are not at the main sequence already. So this star has a lifetime of 5 million years and a mass of 2.3 masses of the Sun, and also has a Keplerian disk with a radius of 550 astronomical units. Here is the image of the continuum flux density that they imaged with ALMA at 0.2 seconds of angular resolution. It's a really beautiful image. And they found 3 dark concentric rings at 60, 100, and 160 astronomical units. And the rings means that they are dust, useless gas on the disk. So they also imaged the molecular emission of 12CO, 13CO, and C18O. These are the flux density of all of that. And there's a problem there because on the images there are no gaps, but in the continuum we estimate that they were rings, so they have to be gaps. Okay, so there's three problems with the image. The first one is that there are no ring structure on the images. The second one is that the C13CO and the C18O have local minima at the center, but the continuum and the 12CO are centrally pitched. So that's kind of weird. And the third problem is that the molecular emission decreases with the orbital value. Okay, the molecular emission decreases with the orbital value slowly than the continuum. So all of these programs they result on the article, and also is like the first approach to know what are going here. So
they use an equation from other paper that from calculate the hypothetical planet mass of the planets located in their rings that we see in the emission flux. For the inner ring, they calculate a planet with a mass of 0.5 to 2 Jupiter mass. For the middle ring, they calculate a planet with a mass of 0.05 to 3 Jupiter mass. And the other thing with a planet of 0.15 to 0.5 Jupiter mass. But,
Yes?
no.
We tell you. So.
No,
Yes,
yes.
okay.
No.
yes. So they made a model to fit their observations, and that's why they found that the rings were at 60, 100, and 160 astronomical units. So the model is the red line on the plots, and they described the model as with three parameters: the distance between the gap and the star, the width of the gap, and the value between the surface density inside and outside the gap. So they use different values for these three parameters, and the best model that fit is on the plots. Yes. So, but they noticed that the density of CO molecules inside the middle and outer gap is reduced compared with the inner gap. So it's like a problem with the inner gap. They don't know what was happening there because they think that it's the three gaps were planets, but the inner gap don't fit with the model really well. Like the model doesn't is not really clear with the observations, so they start to investigate more about it. And
Because of this mistake, can be said, in the model, they study the parameter alpha, known by the Sakura-Sumiraev parameter, and they use this equation of there and find these alpha numbers for all the gaps, and especially in the inner gap, the alpha parameter is relatively high, but my partners explained, in the inner gap there is no CO elevation. It means that in this point they have a higher gas-to-do ratio that implies a low viscosity parameter, that is the alpha parameter, and there is a contradiction between these two results. The equation shows a high viscosity parameter, but the observations implies a low viscosity parameter. Then they try to resolve this problem. They made three hypotheses. I don't know what to say. One of them is that there are more than a single planet. They say that can be 2 Saturn mass planets or more than 2 planets, but for confirm that hypothesis, they need a more accurate observation with more resolution for resolve better the inner gap. The other explanation is at this point there are MRI dead zone. That means that at this point there are like a different force that generate in the 60 astronomical units, that's the inner gap, generate a trap of dust. It means that there is an accumulation of dust that in the continuum.
1 minute. Wait, 1 minute left, sorry. I don't want to. But,
Okay.
yeah.
Okay. There is an accumulation of dust that generates a brighter ring in the continuum. And the last explanation is at this distance from the star there are the CO is no line. It means that out of this distance, the grains are covered by CO ice. I don't know. So yeah, they're covered by CO ice that makes the grains more sticky. And when they drift to the central star and reach this distance, the CO evaporates, and for that we don't see a CO plate at this point. And again, this change the opacity of the dust at this distance in the inner gap and generate again a brighter ring. But for confirm any of these hypotheses, they need to make better observations, especially for the inner disk. I think that's it. Thank you for your attention. If there is any question.
So what is the explanation that they give for the the inner gap in C18O and 13CO that you don't see in its own CO?
That for the snow line or
No. So this inner gap that is referring to the gap in the that you see in all C3 isotopes, right? So here you have the 3 gaps.
Yeah.
Right, and so this the gap at 40 AU, that's the inner gap.
Yes.
Yeah. But in the I'm taking over here because I am in charge. But but you see that there is also a drop in emission in C18O and 13CO in the center.
They say because there may be over reduction of the data with the emission. Like something like that. We don't understand very well.
No, that's okay. It's a very weird thing to think about. So it's over subtraction from the continuum.
Yes.
And so the way that works, and it's really you see it in more ALMA data. Because remember that your dust particles and your molecules are emitting at the same time. So those of you who actually worked with the line data for the ALMA project, you know that you have to subtract the continuum before you can image the lines. But if the line is emitted from a similar layer as the dust, that means that you, if the dust is very optically thick, that means you start to over subtract the continuum. Essentially, some of the line emission is absorbed by the continuum, and then you subtract the whole thing, so you end up too low. So that is what's happening. But I don't remember in how much detail they explain that in the paper.
No, they say only
It's
that
only
it's
one
over
sentence.
subtract
Oh,
of
I'm
the
sorry.
continuum.
I'm sorry.
Like one.
I think this is there are a few papers where they explain this in a lot of detail with all the radiation transfer. I'm sorry, I didn't remember the papers. So,
Is it too hard to prevent that over extraction from the data release?
no, there's nothing you can do about it because the dust is so optically thick line is emitted from below it. So there's, what you can do is not subtract the continuum, then you're probably overproducing it. So all you can do is, be aware of it, or do already a transfer where you, of the line, where you produce the same effect. So there's no way to correct the data.
So picking comes with that.
Yeah.
Right.
It makes it, which of course makes it even harder to do anything. It's actually one of the problems that we have in RS-48 as well, with the asymmetry. The same thing is happening there with the CO emission. That the line emission is gone at the location of the dust trap, so it's really hard to quantify that vortex that we've been producing. Okay. Well, then thank you.
Okay.
Thank you for your really nice presentation. Also, I like how you did it together. Basically, we're switching back and forth. Okay, so who is next?
Juanita?
Juanita? Yeah. Did you email me your presentation?
Yes.
Okay, sorry. Yeah. And here?
Yeah.
No. No tiene bolsillo. Nada.
Si quieres, te pongo con la bolsita. ¿Te sirve? No, mira eso.
No, es horrible.
Lo pongo en la mano.
Sí. No es lo
Y
más
este.
reconocido, pero sí. Ese sí, todo es.
Hola.
A ver, creo que va a tener que subir todo. Ese es tu micrófono. Sí.
Okay, hi everyone. Okay, give me así. Un aplauso.
Gracias, amigo.
Okay.
Yes.
Hi everyone. Hi, I'm Juanita. My name is Juanita, and the paper that the professor Stan chose for me because I'm having a class. It was the big substructure, a high angular resolution project, and characteristics of angular substructure. But the paper is focused in the characteristic and origin of angular substructure, give some hypotheses about that. And this is some images from the paper, from the it's the same disk, but 18 angular substructure that they study, and this is that there are two of them. So, how I change? Thank you. So, the researchers about exoplanets, information from exoplanets, give a lot of information about the composition, chemical composition, and characteristics in general about exoplanets. For example, the mass, the radius, and the composition in general. But we think, and the researchers think, that there are a lot of diversity about these characteristics from the exoplanets, and that diversity could explain from the formation from the exoplanets in the substructure. They think that. And the recent findings talk about new substructures like the angular substructure and other substructure are the spiral substructure and they think that he could explain the diversity and the origin from the characteristics from the exoplanets, focusing in the study and study the characteristics from this annular substructure. And in general, the substructure, but especially in this paper, in annular substructures. And so the idea from the main idea from this paper is investigate the characteristics from the substructure and try to predict and try to give information about the exoplanets that they are forming around the substructure or into the substructure. And so why the research are focusing in annular substructure? Because they see that the numerical simulation have predicted that a massive enough protoplanet will trigger density waves that will eventually impact and create gaps in the disk. So this is interesting, especially interesting to study the origin from the annular substructure compared to the simulation, because they see that made from the composition from this protoplanet may give information from annular substructure compared to the theory. So exists some hypotheses from the origin from this annular substructure. One of these is the condensation can affect how those gains break up, grow, and earth, which in turn cause dust to accumulate in the vicinity of various snowflakes. And how I thought systematically the research used ALMA sources for a single disk, but he investigated 18 disks. Next, can you?
Yes.
Okay. So before the analysis the substructures, we find some interesting results. For example, the first one are from the all the source. There are 18 substructures, 18 sources. He find 17 substructures for 8. So he find that the substructures are pretty common. And if they are pretty common, is important to research about how what is the origin from these substructures and how affect the general formation and evolution from the disk. Also, they find that there are no clear relationships between the host star and the substructure. Also, as the exoplanets has different and diversities compositions, also the host stars also have a difference in diversity compositions. So he can find relationships between the composition and origin from the substructure and the host stars. And the observer-right substructure are reminiscent of features observed in the simulation of planet disk interaction. That is interesting because he tried to compare the simulations that are already done, and the observation and the analysis use ALMA. And the morphologies are diverse. There are no disks similar. No two disks have similar emission profiles. Have to say that the substructure are a lot of diverse. like the exoplanets are a lot of diverse. The substructures also are a lot of diverse, have a lot of diverse. And got any question?
I don't know if Juanita said it, but what were was it something like what you said, Eric, that he uses like several data that was already taken, or he proposed all this to be observed for us to
Yeah, so this is actually part of the D-Sharp program.
Yeah.
So they proposed for these,
Proposed,
these 20, well, actually 20 days to be observed.
And this is continuing.
And it's continuing observations, yeah. And actually this person is a she, but I mean, you didn't know that, so don't worry about it.
Oh, shit.
Yeah.
Oh, Andrews.
Well, Andrew was the PI, but and Jane Mark is, or was his thesis.
Okay.
Okay. So, next, Catalina, I think I've got your presentation. Yeah. Or, well, we've been doing this for like an hour. Shall we take a short break? Maybe? Is that, yeah? Let's take a short break before we start. So, is that okay? Or are you very excited to get started? Yeah? Okay. So let's take a 10-minute break and then we go.
No, nosotros aquí.
Josh, prende la mientras. Sí. ¿Inventario bien?
Está en un examen médico, por eso pues por eso también nos hicimos la vida.
Vale. Sí. Perdón. You want something? Water, coffee?
Coffee.
Okay.
Yeah.
Here we go.
Yeah.
Should I start bringing him back already?
Yeah.
3 minutes?
Yes.
Well, some of them are coming.
Sure.
¿Y cómo te dio con casos para el proyecto de aquí?
No problema.
¿No te ha ido?
No. Pues desde que te lo principio. Mucho más específico y estaba que empecé de calma. No es como que me ve que son entonces.
No. No, lo mejor es como estos eventos donde uno puede sentarse con la persona que sabe específicamente lo que uno necesita hacer y preguntar.
Vamos a hablar de porque yo me encuentro con todo. Y no tengo nada.
No, pero sí, no, toca hacerlo.
Sí, porque lo que hicimos en nuestra astronomía fue parecido a lo que hicimos el primer día.
El tutorial es básico, pero puede ser proyecto de ustedes.
Una reducción de datos.
Pero como de línea,
Sí.
sí, bien diferente, pero solo es continuidad. También te iba a preguntar, ya han avanzado, porque lo que me interesa es si es que estabas haciendo lo de la cámara de Chile. ¿Cómo van con eso?
Ya vamos a tener los planes.
¿Cómo
Los
están
pies,
haciendo eso?
sí,
Remoto. ¿Quién lo hace allá? ¿Qué empresa allá?
Francesco. Francesco y amigos así todo Francesco. ¿Cuál es el que más está en la reunión? El que siempre le pregunto todo. Y es el que más con amiga y el que más emocionado está con todo.
Pero ya han tomado datos también.
Ahí ya nos vamos a hacer un país. Hay datos para mirar la persona, no poder. Y likes y datos. Y supone que ahorita que lo ponemos, bueno, que yo lo monté, como tenemos el nombre de correo, pues para poder empezar a tomar los datos, también vamos a tomar más datos.
Y los datos salen listos para iRock o como los
No, estamos en nuestro país,
bueno.
porque pues, es más fácil. Porque yo voy a hacer un stick y es más fácil. Igual, Francisco también ha hecho unos códigos o avanzados que apenas estoy entendiendo en su país. Yo quería utilizar una pipeline que creo hay que paper de él, pero pues solo tiene y me entiende donde es más complicado. Pero sí, la idea es que me quería ya
How about now?
Yeah. Okay.
a little bit nervous. Presentations in different languages than our foreign language is pretty hard.
Yeah, I understand. Yeah, so we're trying something else in there. Oh, shit, yeah, this was, okay, I need to go back to. sensitive. I put my coffee cup. That's very
Yeah.
a straight line to this thing.
Ya verifico. ¿Habla poco? Bien. Tenemos dos momentos.
Hi everyone, my name is Catalina, and my partner Natalia is in a medical procedure, so she can accompany us today. So I will present you all this paper. It's a very odd case of a simultaneous case of simultaneous star and planet formation. So for the introduction. Okay, so as you know, as we have seen all week, protoplanetary disks have protoplanets, of course, and we can see them by gaps. But gaps are not the only explanation for planets. I mean, just one planet can form a gap, of course, but there can also be a lot of planets forming that gap. And the star that this article is focused about is the K7 star that is located in Barnard 59 in the Pipe Nebula. It's about 1 mega year old, and it has a luminosity of 1.7 solar luminosities, and it has a temperature about 4060 Kelvin, and the data was taken from near infrared and mid infrared in wave. And most of its surrounding is dissipated, and there is thermal emission from this point of from this star. And so we can see in the paper that we get a gap with a wide gap. It's pretty strange because for this kind of years of life of the star, this kind of gap could not be possible. So for a young object like this, it's a pretty big gap. And as we can see later, the accretion of the disk is probably not finished. So, okay. So for the observations, as I told you before, the observation was made in BHG 2007 using both data from ALMA and BLA. And it is located, the star is located in the Pipe Nebula, and it will use a configuration of 22.2 gigahertz of continuum in the K-band and a wavelength of 1.35 centimeters. And it was for the imaging, it was used Kazakh clean and weighing of 1. I won't bore you with these details that are so much important for those who are making observations, so we can just skip it. Okay, so So for the continuum map, that was used 20.4 gigahertz of the bandwidth of the continuum. There were used 44 antennas with two ranging baselines of 15 to 1,460 meters. And the self-calibration was interpolated with phase and amplitude gains, and as you can see, the noise is pretty low for pre-need observation, and the beam is so small so we can observe pretty detailed information of this star. Thank you. And for the spectral lineup, they measure, two isotopes of CO, an isotope of carbon, and an isotope for oxygen. And that cover the source and its surroundings. And the spectral line data is pretty similar from other data calculated in other papers. And of course, as I told before, it has a pretty small noise, and its continuum and spectral line maps they had to incorrect it because the source was a little bit offset from the observation itself. Okay, for the results. So first of all, we can see the substructure of the disk. For the substructure, we can see three little bumps in the picture. Those bumps are the disk, and here we can see a little gap. And of course, in the center, we can expect to be a star. The disk has a radius of 107 astronomical units, and the disk is in edge on. It's not tilted, it's totally edge on. So it's easy for us to see. Now, for the disk CO observations, as you can see, it's pretty similar from the image I showed you before. This is just the CO map. And you can see a flare morphology of the disk, and this emission is more extended than the one we saw before. And for practical and useful information, the C18O was less contaminated than the 12CO data. And when calculating as a Keplerian disk, they measure like a mass around 2.23 solar masses. It's the mass of the star that is in the center of this disk. For the filamentary CO emission, we can see these filaments going up and down from the disk. So they are blue shifted and red shifted as they are in the disk, and we can see in the past slide that they have the same velocity, at least comparable with the CO in the past slide. And they are accreting into the disk, meaning that they are giving more and more mass to the star that is forming. And here is the most interesting data. So in DLA data, there's a thermal emission from the southern space of the source. And there is no other peak here. There is no thermal emission in the northern gap. So I will talk about this later.
Okay.
But can you please?
Yeah.
Thank you for the analysis.
Yeah.
Okay. So for this model, they computed Lightning-Bell and Pringle formalism for a disk, but they didn't. After 100 simulations, they fit this model, but they didn't compare it with real data. They just use it like for, I don't know, for seeing what is happening, but they didn't compare it with the data because it's pretty difficult to compare it. Okay, so as I told you before, the C12 observation were not taken into account here in the simulation, so this makes the simulation a little bit worse than the reality, of course, because we can't always expect to have great models for the things we observe. So let's see, this is a toy model for this data. And so the gap is not in the data that was simulated. The gap is not fully clear, and there are also a lot of problems. So so they have to conduct a lot of more simulations to have into account the thermochemical simulations and other things that they didn't have into account to compare this data with the real data. Okay. And for the potential planet, they found out that the masses point to be a super Jupiter-sized company. As I told you before, the source given by the BLA data was so amazing that they could calculate, like it could be a super Jupiter or a small brown dwarf. Yeah. And as I told you, the uncertainty in the determination of the particle mass and the disk viscosity couldn't make that we have a very large range for masses, from Jupiter masses to 70 Jupiter masses. So we don't really know what's the mass of the source. Okay, and finally for the discussion, the filaments of the gas present in the disk are moving in the line of sight. Here is like some example of we can see a little bit that the filament is moving, but as this is in the line of sight of our radar antennas, so of course we can see clearly that moving, but we can see some changes, but not pretty clear. So we just know that it's the material of the filaments are spreading into the center of the disk, but we don't know if this material is moving around because it's in our line of sight. And finally, no.
Yeah.
Fine.
Okay.
And finally, so as I told you before, we have three main evidences of that there is another source different from the star that is there but we don't know if it is a brown dwarf star or it's a super Jupiter, because we don't really know its mass. From 4 Jupiter mass to 70 Jupiter mass, we don't really know. So there's a presence of the hot spot, and as we can expect from a planet that is forming, we would expect that it would be radiating some energy, so we can expect a hot spot. But of course, a brown dwarf would also be having a hot spot of energy. And the presence of this marginal source seen by the BLA, but not with ALMA, so they have to do another observation with ALMA to corroborate and have more information about the source in this gap. And finally, some of the conclusions. So we can see, I already told them all, but I will explain it again. So we have accretion from the filaments of the disk, and we have a pretty big disk with a pretty huge gap, and we don't really know what is making that gap, but we estimate a little bit its mass. And the compact and warm gas is detected, so we know it's something, but we don't really know what is this something. So, and this is the really good question from the article. Can planets form before the disk itself is purely formed? So if the star is accreting material and the protoplanetary disk is there and it's forming a planet, can we have a formation of planets in the same time as we have the formation of the star? And that's the main question of this article. And so thank you for your attention and some references for this presentation.
Sorry, I guess you didn't see my hand before. It was a little bit too long, but it's okay. No. So are there any questions?
I just have only one, but I don't remember if you said it in the presentation. The gap is how many astronomical units from the star?
I think it's, I didn't say 0.3, 0.7, I think.
Okay, it's near the star.
Yeah, it's near. It's pretty near. That's also pretty strange. Such a big object so near the star in the formation of the star.
And so you mentioned a few times ago that the companion could be a brown dwarf.
Yeah.
So what is the threshold then?
They don't know. They didn't say that.
No, I mean, so what? So from what mass do you call the brown dwarf?
I think it's the 70 Jupiter mass or less.
That's less. So
50? I don't
it's
know.
more like between 15 and 20. Yeah. And it's I mean, this is something that we often see in systems, that we get these pretty high estimates of super Jovian planets when you get in the brown dwarf regime, and some people are like less interested. But dynamically, it is of course not that different, and maybe even formation-wise, it may not be that different. But one thing to consider there is that brown dwarfs are more rare than super Jovian planets and more rare than low mass stars. So kind of like very low mass stars are like 80 Jupiter masses and up. So this is also called the brown dwarf deserts. So that's, if we would find, like essentially if all these large gaps are caused by brown dwarfs, that would be weird again as well, because there's not that many brown dwarfs. But as you say, there's this really large uncertainty in the derivation of the planet mass. So we just Okay. Yes, next. So we have Felipe. It doesn't hurt to say next for you. Okay.
Good morning, everyone.
Wait, please.
Can I wait?
No, you're fine.
Okay.
Good morning, everyone. My name is Felipe. I study at Industrial University of Santander. And today, I will talk about characterization of ring superstructure in the protoplanetary disk of HD 169142 from multi-wavelength ALMAC observations. The principal author of this paper is Enrique Macias. This paper presents a multi-wavelength analysis of the multi-ring disk using ALMAC observations at 0.89, 1.3, and 3 millimeters. In the paper, the observations using band 7, band 6, and band 3. And these figures are continuing observation, and the first in 0.89 millimeters, and second 1.2 millimeters, and 3.1 millimeters. Observation results, this figure use band 7 and band 6, and this is the result, the azimuthally average interference intensity. And yes, this is the ring. V1 is inner disk, and V2, V3, and V4 outer disk. And this is average intensity. Again, V1 inner disk, and this is 0.89 millimeters, and this 1.3 millimeters, and this is 3 millimeters. This chart average radial intensity profiles the observations. Here the model has 51 free parameters, and this is optical dip, and this is the power of the dust opacity. Here is 0.89 millimeters,
and this 1.3 millimeters. Here, the model residual image in different bands in their analytic model. The discussion, this is optical depth profiles in different bands of the observations. Here, here maximum grain size, and the next the red solid line indicate the medium of the position at each radius, and the conclusions are the observation at the three bands clearly resolve the characteristics double ring morphology of HD, and the results of the analysis strongly indicate that the ring substructure in HD are the result of buildups or accumulation of layers dust particles, and their results strongly support the planet origin scenario in agreement with other recent studies on HD. And that's it, is the reference.
Cool. So what is Cosmic Fest UIS? Is that a cartoon?
It's my university now.
Oh, okay. Sorry.
Yeah.
So where do the cartoons come from? I think that's really nice. The graphic from the guy. Is that a famous cartoon figure?
No.
No?
Probably the sign. It's nice.
Okay. No, it's really nice. So what are the grain sizes that they infer in this?
Sorry.
What are the typical grain sizes that they infer from their analysis?
Here? Or
Well, so they do the analysis, like they do the multi-wavelength analysis. In order to solve this problem of optical depth, right? We talked about this earlier this week, that if your dust becomes optically thick, you can no longer relate the emission to grain growth, except if you have 3 or more wavelength observations, which is what they do. Because then you essentially fit the optical depth and the grain size simultaneously. So what is the grain size? The typical grain size that we find?
I don't know.
So it's actually in that plot there in the middle, you see A max, right?
Yes.
As a function of radius.
Yes.
So this is the parameter that they derived from this. So the red line, the average is between 0.1 and 1 centimeter. So their result is that they think that the grains have already grown to millimeter and maybe even centimeter sizes. And at the same time, they measure that the surface density goes like down by a couple of orders of magnitude. So the dust gaps are really deep. And then what is the third panel? Like what is that parameter B?
Forward of particle size distribution.
Yeah, indeed. So that's the coefficients in the size distribution
So we think that the size distribution is a function of A to the size to the power minus B. So that tells you how quickly the slope of that size distribution changes. How quickly it drops. Oh, sorry. Okay. Thanks a lot. Then who is next? Diana? Don't we? Yeah, that's you. Okay.
We do a little test.
Yeah.
Estamos listos. No quiero perder el sensor. Does that look good? For the transmission? Am I outside? Okay. Yeah, I don't want to mess it up. Okay. So my name is Jerónimo. I was reading this week this paper by Miriam Benisti and her collaborators. That's called a circumplanetary disk around PDS-70C. So let's start with it. So this is PDS-70. It's a system that has been characterized before to having a spectral type of K7, stellar mass of about 0.8 solar masses, an age of about 5 million years, a bit more than 5 million years. It's about a bit more than 100 parsecs away toward the constellation of Centauri. And it's part of the Centaurus Lupus association. So here we can see this ultra-wavelength image. I think this is the infrared. I don't know if it's correct.
This is a single wavelength.
Infrared by Muller in 2018. So it's a system that had been observed before and had been seen that it had this disk possible protoplanets orbiting disk. So it was discovered that through H-alpha detections in 2018 and 2018, it was reported that they had a couple of protoplanets that were actively accreting material from the disk. So here we see the work by Wagner in 2018 and Haffert in 2019 that showed the two blobs that confirmed the detection in H-alpha. So yeah, before I read that it was a little bit difficult to make out the detection for PDS-70C, but through work made by Haffert in a little bit higher resolution, they were able to find it and confirm the detection. But now let's talk about what they did for this paper. So they were working with Alman observations of cycle 7. This was band 7 with this configuration. So this is the antenna configuration that were used to take this data. They're working with this mainly this spectral windows to detect 12CO and HTO plus these frequencies. So I kind of like to check this out before working with radio observations to see how is the setup of the observation. So yeah, then they decided to reconstruct the continuum images for PDS-70, and they obviously got this beautiful disk around the star. But then they saw this first image is the same as the last one, but this one is annotated. So you see there is like an inner structure, and in the middle there is this big gap that is carved out by the two planets B and C, and then there is this outer disk. So what they are trying to detect more precisely in this work is that there is another structure around the planet C that is a circumplanetary disk. So it's an accretion disk around the planet, where the planet is capturing material from the disk. So the gas is being accreted right here. So they were trying to reconstruct that. If you remember how to calculate dust mass from your intensity, we derived this on Tuesday, I think. And some other of my fellow classmates have shown this relationship earlier, and they measured this intensity that is reported right here, and they say that this leads to a couple of possible. This is the intensity of the circumplanetary disk around C, around the planet C, and this leads to a couple of possible values of mass of that disk, of the mass that is around the planet, dust mass. But it depends. Each value depends on the size that you assume that the grains should have. So we go from 1 micron grains to 1 millimeter grains, and you get these different values. And if you remember, don't forget about dust trapping. The thing that could lead to having these different values of dust mass around the planet is that if you remember, if you put a protoplanet here, it will create a pressure gradient that will trap dust here in an outer part of the disk. And essentially, what they were saying while analyzing the data is that this probably trap more effectively the grains that were of larger size. So the bigger grains get trapped here, but the grains that are smaller are probably coupled with the gas, and the gas can still flow and escape the particle trap and still accumulate around the planet. So the planet was probably creating more dust material that is of particles of smaller size, and this leads to a different opacity. So you don't work with the same opacity if you have a smaller grain size than if you have a bigger one. So that's what changed the value of the mass of the dust that was around the planet. So don't forget about that possibility. Dust trapping, important. So yeah, here's a beautiful image that was part of the press release that they did, and I was mentioning to Yuki when I was assigning the paper that it was a nice result to me because I was in 2021 attending a virtual school on discs. It was just this free school free event that NASA Exoplanet Science Institute organized. And one of the lectures was announcing this result. So it was very interesting to see it again here and try to read it more thoroughly and explaining it. Because as you can see, there is the detection of the planet here in this reconstruction, and you can see the material orbiting around, where they propose that it's very likely that this is a part where even the protoplanet could be generating around itself like a shock region where there is also a pressure gradient that traps material and starts growing dust sites, like the dust, the grains start to clump together and become a larger object, and maybe could be even a protolunar disk, so something very interesting. It's not yet very well supported by the observations, but it could be something that is happening and is possible in the simulations. So it's a very interesting result. Just try to make it very short and very easy to follow. In conclusion, what they mainly try to take away from the article is that PDS-70C has a confirmed circumplanetary disk, There was tentative detection of this disk before by Isela and collaborators in 2019, but they just suggested that it looked like it might be there, but they didn't confirm it. Now it is confirmed by this work. They also tried to find if the other planet, the planet B, had a circumplanetary disk, but they couldn't confirm it. They say that it's needed to do higher resolution observations in order to confirm that, because with the data set that they got, the observations that they proposed, even the disk around B kept looking like a point source, so it was very compact. So they say that if there is a disk there, it is probably smaller, so it's very small in mass and size. Also, an important conclusion: this system is great. BDS-70 is awesome. It is first for a lot of things in circumplanetary disks and in disk physics. I don't know, it's very useful to characterize circumplanetary disk, to understand how our planet-disk interactions. They're saying that you can use kinematic models and further observations with ALMA in the following decades to follow the orbits of the planets and understand better how these real planet-disk interactions in these real systems. And also understanding disk cavity clearing, because you can see how both planets carve this cavity in the disk material. So also they say that CPDs for the future could provide constraints on the formation of satellites around gas giants. So what I was saying, that you could be forming moons around these planets. So yeah, I think I don't have anything else.
Are there mechanisms that explain how was it formed, the circumplanetary disk?
I think they're saying mainly like the planet like starts to form by putting material inside of the disk, and it mainly keeps gathering. But they say that they see the gap in both in gas observation, like in CO, and in the dust and continuum observations, so that they confirm that it's a gap that is carved by the planets, because the planets are capturing material. And the main mechanism that they argue is there is the one that I mentioned, that even though the planet creates a dust trap that keeps the material further away and keeps the bigger grains far away from the planet, still, since the gas is coupled to the smaller grains, the small grains are able to keep falling inward and being captured inside of the planet's sphere of influence. So that's what I understand. I don't know if I'm far off from reality.
Yeah, well, as with many things, we don't know exactly how it works, but there are some people working on this, that essentially if you form a planet and material starts to fit onto the planet, then it will just, it's kind of the same with conservation of angular momentum. You expect the material to form a disk really quickly, and then the material accretes from the disk onto the planet. There is, but I think most of this is still done just in hydro, not so much in dust. So I don't think we have a very good, the predictions are still very limited. Essentially, we need more observational constraints in order to test these models and quantify these models.
Oh, I didn't mention it. Planets are like tenths of AU, so B is like a 22 and C is like a 34 AU from the star. So it's not that large. It's far away, but it's not that large scale that we've seen in other disks. It's hundreds of AU.
Can you remind me how much mass is this simulated planetary?
Well, I don't know if the mass reported is for the whole system. What do you think? It's just the central, the 0.8 solar mass. I'm not sure.
You mean the mass of the planets, right?
Oh, the mass of the planets. I remember because I'm not sure. They said it right here. It's like in the, I'm sure that. It's like. They say it's just on an order of a few Jupiter masses. I'm not sure they mention precise.
Yeah, it's, yeah, so this is based on the earlier observations from like Kepler and Wagner, where so there's the high contrast imaging, where they detected the planets to begin with, or that brightness to a planet mass. So then, of course, you will have a number of assumptions, and to be safe, you usually say, oh, it must be somewhere within this range.
Is there a chance that it is actually a brown dwarf or something?
I think not. I think because they have several observations now also on multiple wavelengths in the infrared. So they have a pretty good idea of the black body of the planet. And I think brown dwarfs are pretty rolled out. The masses are well enough also. That's cool. Yeah. And that's different than what we saw in the earlier presentation, where they estimated the mass of the planet between 4 and 70 Jupiter masses. But that was not based on planet detection, it was just based on the width of the dust cap. So those estimates are obviously more uncertain. Okay. Thanks a lot, Hannah. And then I think going to the last. So Anna Sophia is next. And I don't know if did I miss anyone?
I think we're done.
I think that after Anna's, so that's the last presentation.
No,
Oh, yeah, you don't have.
I'm from Canada.
Which one are you? Sorry. Of course. Then you're next.
Okay. No,
Cool.
Be careful with the cable, please.
Oh, okay. Yeah, go ahead.
Okay, so good morning. My name is Ana Sofia Marulanda Duken. I'm a physics engineer graduated from Epic University, and today I'm going to talk to you about this article that I read this week, which is called Variable H13 CO plus emission in the ion lattice, X-ray driven time-dependent chemistry, and it's a research done by the Harvard Center for Astrophysics and the University of Michigan. The reason why I chose this article is because I do like X-ray astronomy and I wanted to learn more, even though I didn't know much about this chemistry on this type of systems, but I wanted to get myself into this challenge. So first, let's review the purpose of this research. Basically, we have been talking about key molecular items, right? HCO plus and all of the ones that we trace in order to see events on disks. And on this article, they have the HCO plus and the H13 CO plus, and which we can observe the rotational transition, and that way we can get data. So this is our object, which is ion club, and it is a protoplanetary disk around a T-toroid star. Basically, what they did was 3 observations. During the two first ones, they observed a normal line flux. But during the third one, they realized that actually the flux doubled, and they were like, why is this happening? This is a brightening event. So they realized, okay, we have an X-ray active star, and it is continually irradiating the disk via stellar flares, which is enhancing the molecular ions that are present. So if this actually is true, future observations should be able to resolve these events and also allows us to explore ionization physics and chemistry on disks. The introduction is basically that key molecular ions are very sensitive to high energy processes that are continually occurring on the protoplanetary disk. And right now we have T-toroid stars. These stars are not like the normal ones like our sun, that if we get the luminosity, we are going to get a continuum over time. This is not the case. Basically, these stars are very, very variable, and we can have very strong luminosities, and if we measure like months before, we're going to have a different one. And the characteristics are that they are very young, they are very low mass, like minor than 3 stellar masses. They haven't even gotten to the main sequence. and they have a continued and an actively accreting disk. So what happens for the X-ray production is that the material falls along the magnetic field lines from the disk into the star, and then the plasma gets very heated up. When this happens, the X-rays are emitted. So this variability on these stars can be of two ways. The first one is a very long variability, which is due to accretion and magnetic field. And the short variability can be due to events in the corona, like for example, our sun that has these storms or flares. So they were like, okay, we have this phenomena and this element, does the bulk chemistry respond to this? Actually, the ALMA observations show that it does. And this is what we are going to take a look at today. The observations that we have are not only from ALMA telescope, but also from the SWIFT mission, because we also need information from X-ray and far UV. The ALMA observations were done on 3 different dates, but of course, because what the professor mentioned before, we do not have like continuum campaigns of observation, but we need to take data from different campaigns of observations, right? So we have the 2014 and 2015 observations. These are like the parameters that were used, like the baselines, the number of antennas, and the time each one of them spent on the source. These are the elements that were used to calibrate the system. So for example, for the first observation, we had a self-calibration with the continuum measurement on the disk. And on the second and third one, this quasar was used to calibrate the band pass, and the Titan was set to the amplitude scale. These are the results that were obtained with ALMA. Here we have the 3 observations, right? The first, and of course, because there were different campaigns, they were not the same. So there needs to be some adjustment done with CASM in order to have the same disk and to be able to compare them. So we have the continuum, and the red lines are contours that are from 50, 100, and 150 microjansky, which are the fluxes. Here we have what they observed and what is driving this whole study, which on red and yellow, you can see the first 2 observations on the flux, and they say, okay, this is normal, this is like a normal event, but the blue one is where they say, okay, we have the double flux. Why is this happening? Here we have before the continuum extraction, and even it is visible. The blue one is the third observation. After the removal of the continuum, we have that there is definitely a jump on the flux. Now, in order to get the X-ray information, they access to SWIFT information. And on the SWIFT mission, they use both the XRT, which is the X-ray telescope, and the UVOT, which is the ultraviolet and optical telescope. These are the dates for the observations, and of course, the X-ray spectra was extracted using the SWIFT Science data pipeline, and the photometric UVOT measurements were extracted using the high-energy astrophysics software. These, of course, are the results, but they needed to normalize them because we are trying to compare different measurements, different scales, of course, X-ray scales and the gases scales. So they normalize it, and here we have the red line, which is okay, this is the event that happened during the flare. In order to feed this data into a normalized one, we integrate the model X-ray spectra from 1 into 10 kilo-electron-volts in order to obtain the total luminosity per observation, always assuming a distance of 161 parsecs. From these observations, they realized, okay, so the ion that we are looking for is actually consistent with the optical beam. And we can attribute the changes on this flux to changes into abundance. So of course, if we have a doubling on the flux, it's because this molecular ion must be higher. Also, the X-ray fluxes measurements are affected by multiple flares because we do not have like an isolated flare, but we might have multiple of them. And because the stellar variability is not very easily predictable, because these type of events just happen randomly and have very erratic behavior. But we do have an active time variable X-ray star, which has a very high increase on X-ray luminosity. So they said, okay, we have these observations, but now we want to compare them with chemical models. These are the reactions that are governing the formation of this ion in the atmosphere. Here, the H3 is produced by the X-ray ionization of H2 plus in the surface layer. And these electrons that are combined here are occasioned by photoionization. So what they are trying to do with these chemical models is to explore chemical evolution in 3 different gradients. We have 25, 50, and 100 astronomical units. These are the results. Basically, here we have the parameters that they put into the model. We have different derivatives and the altitudes, because of course the altitude of the disk, the chemical characteristics vary. We have the density of the gas, the temperature of the gas, and the temperature of the dust. Here we're going to take a look at this later, even better, but actually we can observe how H3 abundances respond immediately to X-ray flares. So if there's a flare, we can immediately relate to the abundance of the flux. And of course we can expect, because it happens with H3 and HCO+, we can expect for H13CO+ to behave the same way, according to their characteristic, their chemical structure, right? So here we can have it bigger. We can see that the gray line is like the peak of X-ray, and the yellow one is for an altitude of 0.5, and the red one is for 0.4. We can see that the red one has the strongest response to X-ray flare, but they last for a shorter period of time. Here, the red line dissipates even faster. And the yellow one, we can see that it actually has 2 orders of magnitude to be more attenuated, but because we have an altitude of 0.5, we have a higher density electron, which made them last longer. You can see how they dissipate even like longer. Yeah, 1 minute, perfect. With this, we can find the local electron density, which is why we're trying to measure in order to understand better the chemistry of the disk. And they found that the estimation, with of course the number in here, they found that the electron density is 2.7, and the chemical model actually gave us one of 3.3. So there is a very short difference, but actually can be attributed to the lack of temperature information. Now, finally, the discussion we can have that we have the detection of significant variability of this isotope load in the ion load disk. One possible explanation is the enhanced ion chemistry during the X-ray flare, but also the length of the X-ray flare is very important to keep in mind. This is the first robust evidence of sub-millimeter variability. We have a better understanding of this ionization chemistry, which turns out to be more dynamic than we previously assumed. This provides, of course, a new tool to understand better the disk physics, and for example, accretion physics, thermal structure, and the disk chemistry. We have also a new method to estimate the disk spatial ionization fraction. So these are like at the end, the conclusions that the article came up with. These are some references that I used for this presentation, and I wanted to highlight these 2 other articles which allow me to understand even better, because some things were complicated, so I wanted to read more about teacher stars and about these disks. So yeah, this is my presentation. Thank you.
Any questions? The paper that you presented is from 2017. That's already 5 years ago. Did they mention that they want to do any follow-up observations?
No, they only like mention what we can do with ALMA now, like only if we target our observations into this kind of information, and how like if we set some new configurations and some like I think it was 11 days of observation with some configuration, we can have even more information, but they did not mention like they wanted to have a higher reach with this specific research. So yeah, I did not see that.
Okay.
Okay, thank you.
Thank you. So then the next is Juanita. Yeah.
Yeah, apparently it's called apparently it's called the virus. Here, yeah. So it didn't deliver. Okay.
So,
And
I'll
okay,
tell them a number, or,
yeah, well, or you can connect your laptop to the AC line. You don't, maybe that's faster. And maybe check your computer for viruses. Yeah, this is the virus scanner from the Leiden mail server, so it says that there is an issue there. Yeah. I think you need to drag it to the left. I mean, it depends on how your desktops are set up. To the right? Yeah, to the right. Okay. Yeah. And okay, so you don't have you also have UVC, right? Okay.
Wait. Wait for it.
Okay, so hello everyone. My name is Alejandra Calderon, and I'm presenting this paper, Kinematic Detection of Planet Breathing a Gap after Planetary Disk, from Pink et al. Well, so I'm going to talk about some previous definitions first, then a little bit of summarize of this paper, the results they got, and the discussion. This is pretty important for understanding the article. I took these images from the professor's presentation. So this is a vertical heat type. Basically, what is important about this is to having to take into account these two like different color zones that are shown because of this emission surface. And the velocity kings, this is pretty important in this paper. This is the velocity king, this one is right here. This is supposed to be like continuous like this one, but you find here like there is some sort of disrupt line, and here it can be seen in the velocity spectrum, and these velocity kings are seen as the blue shifts and the red shifts, and that one over there is like a scheme of all of this. And well, the circumplanetary disks are those small disks that are contained in the big disk, and it can be seen as a blue shift and a red shift in the receivables of the Doppler flips of the CO spectrum. And well, the summarize of the article, what they did, and I'm going to talk about a little bit of the context, the thesis statement they had, and the methods they used to do this. So this detection was not only made with ALMA, but with the Sphere telescope, as my classmate said, because it is needed to confirm this observations in UV and X-ray. And they find it, there was a gap in the disk, and they proposed that it was caused because of a planet. This disk is supposed to have two different planets, but in this paper they just studied one of them, that is the one that is farther from the star, and is estimated to be located in this cyan dot, and with this uncertainty. And basically. And so they studied this star that is a AE or BE type star, and is surrounded by a giant disk that has gaps and velocity kings, as we saw before. And they studied the kinematics of this disk, and they find that it was a localized deviation from the Keplerian flow, a velocity king, and a gap. And they said like the most possible thing that could be there to cause those three localized phenomena is a planet with a Jupiter mass. And there's also something important about the dynamics of this disk that is basically measured by this Stokes number, that what it actually does is to tell you the behavior of particles suspended in a fluid flow. And so, the methods they used, they observed with ALMA in these 3 different days to have a continuum, and they used this beam size observed in the 7 band, and they saw that the velocity king is only visible in a few channels between 0.7 and 1.1 kilometers per second. As you can see, the velocity king is here, and here, but in the other observations, you don't see the king. They did a 3-dimensional model procedure in which they divided the particles in 11 groups and evolved simultaneously all of these groups with the gas and with this phantom code. And they set the artificial viscosity to find the Sakura-Sunyaev viscosity parameter that was mentioned in other papers. And an important thing here is that planets have an accretion disk, and so their masses are supposed to increase, but they fixed the planet masses. They found that the planets accrete a moderate amount of gas, but the migration is negligible. And they did the thermal structure with Monte Carlo radiated transfer code. And there is something important here that is what other classmates mentioned in their papers, that you can subtract the CO emissions. These are the subtracted emissions that are in an additional paper, not in the paper that I'm showing you. And they basically did the subtract CO emissions for 2 Jupiter mass planet, and just to show that you can see the kink also in the continuous subtract CO maps. These are the subtracted CO maps, and these are the non-subtracted CO maps. And also the emitting grains are pretty diverse, and there must be fluffy aggregates, to increase the Stokes number. And this is a simulation with a Stokes number of 1. This has a 10 to the minus 2 Stokes number, and this is actually real observation with ALMA. Well, the radiative equilibrium hydrodynamics calculations, there are different models to calculate the dynamics. And the velocity of fields of a 2 Jupiter mass model could be calculated the velocity with a vertical isothermal model or a vertically stratified model. And this one, the second one, is a little bit more complex because they had to do more iterations, and the code is a little bit more complex. And here you can see that both methods give similar results. So they took the vertically isothermal model. And this was azimuthal velocity. You can see that radial velocity doesn't change either, or vertical velocity. And the UV plane sampling, they clean data with Gaussian convolution with CASA. That is basically what we've been doing. But there exists other types of cleaning, and this cleaning was like a modified process that is not exactly a Gaussian convolution, and they add thermal noise. And as you can see, this is a little bit more similar to the observations, but this shows the keying and all of the these properties that we wanted to study. So they did Gaussian convolution in all of their paper. So the results. First, here we have the first figure, and is showing the ALMA observation of the velocity kink right here, and also shows the continuum and the dust and gas disk surroundings. Here in the blue dot is where they expect to be located the planet, and it basically is located there because it's where the gaps, the velocity kink, and red shift and blue shift are located. So it's like the intersections of these three phenomena, and that's why we think the planet is right there. As you've seen before, this figure is basically about this paper, this. So as you can see, there is the CO lower surface and the upper surface. And in both, you can see the emitting CO, but on the upper one, you can see this little kink right here. And this is the kink zoom. This is a hydrodynamical model for a 2 Jupiter mass planet interacting with this, and as you can see, there is like this is spirals, and the redshift and blue shift. And here they took, basically, as I said, as I mentioned before, there are 2 planets in this disk. But they just changed the mass for the outer planet. The inner planet, they took 1 Jupiter mass, fixed mass for that one, and they used 1 Jupiter mass, 2 Jupiter mass, 3 and 5 models to, see which one fits better or is. They conclude that this planet must be a 2 Jupiter mass planet. Okay, cool. So these ones are the references. And
I think I don't understand yet.
Why did they changed the mass for the inner planet?
because it would have been pretty complex.
Changed the mass for the inner planet.
Because it would have been pretty complex. Like, as you have seen here, changing just this mass changed a lot the model, and it will have a lot of parameters that would like interfere. And I mean, it was like easier to start here. I don't know if they didn't mention, but this paper is from 2018, so I don't know if anyone has done what you said, changing those 2 masses. And basically because this planet has a king that is a little bit more visible. The other one has not all of this phenomena of the king, the god. So it's more likely to be a planet, this one. The other one has not all of the characteristics and could be, as we saw before, vortex or just pressure, but it's not certain to be a planet.
I think I didn't understand quite well what the kinks are. Is that like inflowing material or outflowing material because of the direction of the planet?
Are just changes in the CO emissions. These are like the normal CO emissions and the emissions, and the king is like this change in the emission. You can see it here. It's like not continuous CO because of this difference on the pressure, because of the gap, and it sort of distortions a little bit the CO.
Not inflow material, it's the dynamics of the disk that are disturbed because the planet is there.
Okay.
Okay. Thanks a lot. Yeah, these were 2 good questions. I don't know further questions. So thanks everyone for all of your presentations. Let's do one more. I hope you all enjoyed that. It made sense also in the context of all the topics we discussed. And so on the program, that we're going to have one more lecture for me on exoplanets, but of course we take then again a little break now. My lecture is not going to be 2 hours like the previous ones, it's 45 minutes. So let's do a 10-minute break. Then I'll give my lecture, and then my 1 o'clock we're going to have our lunch break. Is that okay for everyone? Yeah. Yes. And something tell me where the bathroom is because I'm.
Yeah, sure. Just right down the hallway. Any either side.
Okay.
Yes.
I just have to go.
No, pero me sigue porque.
No, bueno, no es una
Entonces,
Entonces, ¿cómo es la dinámica? Estamos 10 minutos. Y luego, lecciones
charla de 45.
45 y salimos a las
A la una,
como las 1 de la tarde.
almorzar. Y ahí volvemos.
Listo.
Me para apretar. Dale, metí todo el esfuerzo para eso. Los resultados ahora están confusos.
Hicimos bien.
No hay.
Y luego las caras de resultados.
Espero no sea proporcional
Muy bien, todos.
a la presentación.
Por lo menos de los resultados del proyecto.
Pero es más fácil decirlo, ¿no?
Ah,
No hicimos.
vamos con la
Sí.
Yo en poco tiempo, no sé exactamente cuándo me tengo que ir. Entonces estarán encargadas allá.
Ah, bueno. Entonces para que todo cerrar y
Sí, entonces cerrar y volver a abrir. ¿Listo? Ya para salir, entonces le das allá es que el plan está cerrado. Entonces se la. Es que Frank se fue. Se la dejas a Frank. Listo que.
No, pues que
¿te la recibe?
No, pues que no, acabas de decir mujer.
Ah, no, pero se fue a avisar.
No, vi que se me fue.
No, pero él está encargado de todo lo demás. Entonces.
Yo quedo de paso.
¿Yo qué hago con los equipos de transmisión?
No, pero de eso está encargado Frank.
Todo.
Todos. Pero ahorita inmediatamente.
Ya,
se quedó.
¿Alguien saca un rato con el break? Lo cerramos.
No, sí, pues cortemos acá. Un placer.
Y no había y no se le ocurrió, ya no hay.
Vale, vale.